In this video, I want to take a look at what happens when you plug a complex number into an exponential function. Okay. And the reason that I need to look at this is because we're solving differential equations of this kind. So we got second order linear with constant coefficients a y double prime plus b y prime plus c y equals 0. And we started doing these by saying, hey, let's look for solutions of the form y equals e to the rt. Right, and you plug that in, and you end up having to solve the characteristic equation, which here is this quadratic equation, ar squared plus br plus c equals 0. Now, we can use the quadratic formula to solve that, and this is the quadratic formula stated here, that r would equal negative b plus or minus square root of b squared minus 4ac all over 2a. And there's three potential outcomes here. One, if b squared minus 4ac is bigger than 0, then you can take that square root and you get two real solutions. And in that case, we've really already discussed that. You'd have e to the first real, you just plug them in here. Those two real solutions would be plugged in for r. And then we take a linear combination of those, c1 times the first one plus c2 times the second one, to get the general solution to that differential equation. Second thing that could happen is that b squared minus 4ac could be 0, and you only get one solution here. And the third thing, which is the one we're going to look at today, is b squared minus 4ac is a negative, and so you're trying to take the square root of a negative number, and you're getting imaginary results. Or it's called complex if it has both a real part and an imaginary part, which this would have. The negative b over 2a would be the real part, and this square root divided by 2a would be the imaginary part. So, what would it mean to do e to some imaginary thing times t? What kind of function is that? Well, that's what we need to look at. And there's really two ways that I approach this. One is a sort of an algebraic geometric approach, and the other is with sequences and series. So I'm going to start with the algebraic geometric approach. I have to admit that I find it hard to tell the difference between algebra and geometry because I swap back and forth between them all the time. To me, equations have graphs associated with them, right? So you can take a look at what's happening rather than just doing the algebra. And sometimes the picture helps you understand the algebra, and sometimes the geometry problem is too hard, so you turn it into an algebra problem and you solve it that way. Anyway, I go back and forth all the time. Okay, so here we go. Complex numbers you probably introduced to back in a pre-calc class somewhere, but you really haven't had a lot of chance to use them yet. Well, here's your first chance to really use them. So I'm going to remind you what they are and how we work with them a little bit. The complex numbers don't come in a line, they come in a plane, or at least a good way to interpret them is in a plane, and you'd have like a real axis here and the imaginary axis there. And every point in the plane corresponds to some complex number. So this blue dot would be the number a plus bi, where a is the real part of it, essentially the x direction, and bi is the imaginary part. So each complex number has a real part and an imaginary part. I can also think of them in polar coordinates, where you have r would be the distance from 0, the origin, and theta would be the angle made with the positive real axis here. I'm going to try and not call it the positive x-axis because it's not x and y here, it's real and imaginary. So a plus bi could be rewritten this way, just doing some trig. I'm going to ask this many, many times. How's your trig? Well, I know that there's a relationship between theta, a, and r. That is, the cosine of theta is a divided by r. So a would be r times the cosine of theta. Now, I'm using r1 and r2 because I'm going to talk about two different points. So r1 might be this one right here. Okay. So a is the radius times the cosine of the angle. And the other side here, the length of the other side, is the radius times the sine of the angle. So the real component would be r1 times the cosine of theta, and the imaginary component would be I times r1 times the sine of theta. It is quite often the case that we would write this by factoring out the radius, just have the radius times this. Now it turns out that this part right here, the cos theta plus I sine theta, is actually talking about a point on the unit circle. Right? Essentially, parametric equations, x equals cos theta, y equals sine theta, describe the unit circle. It's just that this is the unit circle in the complex plane. And then you multiply by r to scale out where you need to be. So anyway, I've got two complex numbers that I want to look at. I got a plus bi and I've got c plus di. The only difference in the polar coordinates is, of course, that they have potentially different distances from the origin and they have different angles from the positive real axis. Now, the geometry that I want to look at is what is the geometry of multiplying two complex numbers together. When you learn this in a pre-calculus class or something, you maybe learn this right here. You learn that you just FOIL it, right? How do you multiply two things that look like this? You FOIL them. So you got A times C, I got A times DI, I got BI times C, I got BI times DI. I get these four things. But then I use the fact that I squared. Well, I is the square root of minus 1, so I squared is negative 1. And so the BDI squared actually becomes a completely real part. And the real part of the answer is the AC minus BD, because the I squared turned into minus 1. And the imaginary part imaginary part of the answer is the sum of these two pieces, right? So factor the I out. And there you go. And that's pretty much all you would see in a pre-calc class is that's how you do it. That's how you multiply them together. What you don't see is the geometry of what's going on. And that's where I think the polar coordinates really show us the geometry. So I'm going to do the same calculation where I've got a plus bi times c plus di. So here's the a plus bi, and here's the c plus di, just written in the polar forms, and I'm multiplying together. But now what I have is I've got four things multiplied together, because this is one number times the stuff in parentheses times another number times the stuff in parentheses, and I can multiply those in any order I want. So I'm choosing to put the R1 and R2 out front, and then I'm going to multiply these two things in parentheses together, so there's a FOIL that happens there. So I'm going to have the cosine theta cosine phi, there's my firsts, cosine theta I sine phi, that's the outsides, I sine theta cosine phi, that's the insides, and the last would be I squared sine theta sine phi. Okay. And again, the I squared is going to turn into a minus 1, and so the real part of this solution is this first term and the last term, but with a minus sign in between. And the imaginary part is the sum of these two here, so factor the I out, you get this. Now, how's your trig? Do you recognize any identities here? Cosine theta cosine phi minus sine theta sine phi? Yeah, that is the cosine of theta plus phi. And the stuff in parentheses here, cosine theta sine phi plus sine theta cosine phi, that's the sine of theta plus phi. So what happens is the product of these two things ends up being another complex number in polar form here, right, where the distance from the origin is the product of the original two distances, and the angle that you turn from the positive real axis, is the sum of the two angles that you started with. Okay? So multiplying two complex numbers multiplies their lengths and adds their angles. This is really cool. This is really, really cool. There's lots of stuff you can do with this because multiplying is just rotating. Right? If you multiply by something on the unit circle that has length 1, you're not changing the length, but you change the angle. So I've done many animations by doing rotation by multiplying by complex numbers. Anyway, there's another way, it turns out, that I can do this multiplication where part of it multiplies and part of it adds. So just for sort of like a thought experiment, what if I were to say, let's let e to the I theta equal, essentially, that stuff that was in parentheses here, cos theta plus I sine theta. E to the I theta, I want to let be cos theta plus I sine theta. Because then I can rewrite the a plus bi like this, r1 times. I mean, I'm just writing the same way, but I've chosen to, for whatever reason, make the stuff in parentheses there equal to this e to the I theta. And so likewise, c plus di would be r2 times e to the I phi. But notice what happens when you multiply these two things together. How do you multiply those? Well, it's just multiplying the you got four things being multiplied together, so do it in any order you want. So put the r's out in front first. And then you got the product of those two exponentials. Now, how do you multiply two things with the same base? You keep the base and you add the exponents. So I'm multiplying, yes, but in order to accomplish that multiplying, I have to add certain pieces of it. So this ends up being e to the I theta plus I phi, and you can factor the I out, and it looks like this. Well, if e to the I theta was cos theta plus I sine theta, then e to the I theta plus phi should be cos theta plus phi plus I sine theta plus phi. And what I've done is I've done this whole calculation right here, all this polar coordinate stuff, I just did right there, right, really quickly, because e to the I theta is behaving exactly like cos theta plus I sine theta behaved. It multiplies by adding. Right? You multiply the numbers by adding the exponents. Anyway, so that's cool, but it's kind of like, really? You just got to just pull that out of the air? Yeah, well, it's not entirely out of the air. So I'm about to run out of time. And so I'm going to cut right here, and we're going to make a different video about the series approach for plugging complex numbers into exponential functions.